So hi everyone, welcome to the second session of the Data Science Guild. Today, Asaf and I will tell you a bit about the iterative methodology for personalization models optimization. So Asaf is leading the NLP and user profile team. I'm leading the personalization team. Okay, so our agenda. We'll start by explaining a bit about the settings of our modeling, the settings of generating our model, the settings of the user profile, and so forth. And then we'll see that we actually have several moving parts in the optimization methodology that we're using. And we'll tell you a bit about the offline modeling framework. And then Asaf will explain about the user profile lab. And we'll conclude with some very specific use case of how we added a new feature and how this feature was sort of going through starting from the document. It's a document feature, document semantic feature, starting from the document level, moving on to the user profile, and then moving into the models, and then moving hopefully to production. Okay. So to start a bit about our setting, so I know that probably a lot of you are familiar with our setting in the serving layer. So we have a user coming in, and we have a context, which is essentially the page this user is currently reading, and some more information about the state of the user. And we have an inventory of potential recommendations. And now the goal of the serving layer is to assign scores to all the items in our inventory and recommend the best items to the user. So if we have an organic inventory or a sphere inventory, we just want to sort of recommend recommendations that the user is most likely to engage with. And if we're talking about paid recommendations, then we need to take the CPC into account as well. We're optimizing for RPM. Okay. By the way, if you have any questions at any time, you can just ask. Okay, so what kind of information we have when we are at this point of serving recommendations? Okay, what type of information we have? So the first type of information are the features that we have on our documents or on our potential recommendations. Okay, and here's an example of the semantic features that we have. We have semantic features of different levels of granularity. Okay, we have low granularity features such as categories. It's a taxonomy of about 100. Categories, so sort of general topics on which the content is about. Then we have more granular, higher granularity features, which are topics, and we have very specific features that identify the text, which are entities. So there are specific people or specific organizations, specific location, and so forth. Okay, so these are the features that we have for our inventory, for our documents or potential recommendations. Another type of information that we have is the user profile. Okay, so essentially we have a system that generates user profiles. They are based on the past interactions of the users. What we're storing is the last 100 interactions, the most recent 100 interactions of the user. And we're aggregating those into to create a profile that sort of corresponds to user interests. Okay, and what you're seeing in that profile is, again, several types of features, of semantic features. You can say something about the categories the user is interested in. You can say something about the entities and so forth. So the user here in this example is interested in television and investing. You also have a score, which tells you something about the to which extent the user is interested in that topic. And this specific user is also interested in HBO as a specific entity, and Dolores from Westworld as a specific entity. Okay. So the third type of information that we have is information that we're getting from the contextual layer. And the contextual team led by Ilan is the one that is generating this type of information. So what we're getting from the contextual layer is what are the best recommendations given that the user is currently in CNN.com, for example. Okay, so it doesn't have the personalized level, but it has sort of a ranking or estimated CTRs for recommendation based on a specific context. Okay, so this is also one of our ingredients, of the model ingredients. Okay, and the final unifying sort of piece of all this is the machine learning trained model that takes all the signals together and combines them to apply them on the inventory and to recommend the content. Okay, so this is the setting of the serving layer. So I'll tell you a bit. I won't deep dive into the modeling because this is not our focus today, but I'll tell you a bit about the two main types of models that we're using. So one type of model would be the content-based model. And the content-based model, what it basically does is recommending content based on the similarity between the user interests and the actually the content, whether it's the ad or the document that we're recommending. Okay, so for example, if we have a user, the previous user that we saw, the user is interested in television, actually specifically interested in Westworld because we're seeing like Dolores and its entities. So we'll probably rank the Westworld recommendation higher than some Donald Trump recommendations to that user. Okay, so this is what a content-based model aims to do. A collaborative model is not limited to content match. Okay, what it tries to do is to find sort of a set of users which are similar to the users that we're seeing, and looking at which content this user likes. And it's not necessarily content that matches the interest. It can be something like cross matches and so forth. So, for example, what we can see here is that users that have similar content to that user, a similar profile to that user, are also interested in the TV series Handmaid's Tale. So we're going to recommend that one as well. Okay, and our ultimate goal would basically be, okay, through all this optimization process, we want to improve our KPIs. And our KPIs, our main KPIs would be for paid, we have RPM, revenue per milli. And for Sphere and organic, we have something that is called participation rate, and we have CTR. But it's basically user engagement. Okay, so we have user engagement for those, but when for paid, we also incorporate CPC, and we want to optimize the revenue. And to improve our online metrics, our production KPIs, we basically have three different like sort of moving parts that we can optimize. Again, in the context of personalization, I'm not talking about the contextual layer at this point. So at the context of personalization, we can optimize document features. Okay, we can enhance document features. For example, we can add a new semantic feature, which will be actually our use case that Asaf will describe in the next hour. Then we can optimize the user profile aggregation. Okay, we have all these interactions the user has done in the past, but we have some freedom in the way we aggregate these interactions. For example, we can treat some interactions as more important than others. We can say that we have some features which are more popular in general, and they're less, have less information in them. We want to decrease their weight in the profile and so forth. So we have some freedom of how to aggregate the sort of the browsing history of the user to create a user profile. And finally, we can obviously optimize our models. So it could be by using different hyperparameters or just changing the type of models. For example, moving from content-based to collaborative. Okay, so we have all these moving parts, and obviously the most direct way of checking those would be to A/B test, right? Let's make all the changes that we need, put this in production, and see how users engage with these new models. But we have three problems for that. Okay, A/B testing is very expensive, and it's expensive on different levels. So the first level would be that we sort of jeopardize our KPIs. Okay, we put a model, we don't know what's going to happen. We have KPIs, we can get less money or get less user engagement. Okay, so this is something we don't want to put at risk. The second thing would be, which is expensive, would be full productization requires a lot of efforts, a lot of engineering efforts, and I'll give you an example in a second of even not a very significant change, that it requires quite a lot of changes in our serving stack. So this is expensive in the sense of a lot of engineering effort. And the cycles are rather long, okay, because what we're getting is that, let's say that I want to test some grid of hyperparameters. For each combination, I need to start a new variant in my A/B test. I need to assign traffic to it. Obviously, it can't be a lot of traffic, so I need to wait for a long time to see significant results. So the cycles would be very long to optimize. Okay. Let me give you just an example of, in terms of engineering efforts, what involves, a rather simple change. So, for example, if we're adding a new semantic feature to our document, let's say that we have our NLP engine already generated a new semantic feature for documents, what is required for that feature to actually propagate through, the full flow and be used in our personalization models. So it requires actually three main changes. The first change would be to change the user aggregation and to take this feature into account, right? And this needs to, again, we need to change production systems. We need to wait to this change to propagate through all our users, which can take a few days. So this is one thing. The second effort would be to actually make this feature available for serving. So I don't know, I think at least many of you know that our serving stack is based on Elasticsearch. So for a certain feature to be available for serving, we need to index that feature, and we need to sort of change our index structure to be able to have this feature available for serving. So this is the second thing. And the third thing would be we need to change our scoring function, which is we have our own custom scoring function within Elasticsearch that applies the models, and we need to change it to support the new feature. Okay, so this is rather expensive to put into production. We don't want to do it with each iteration of improvements. We don't want to make this process. And even more significant or more very difficult change could be introducing a new type of models. So for example, when we introduced the collaborative models, to support that in production, it was an effort of a couple of months. And aside from the personalization team, we had another three additional teams involved in this effort to do the full integration. Okay, so it's a rather extensive effort. Okay, and the solution that we're presenting today, Asaf and I, would be how to sort of shorten the cycle by using offline evaluation frameworks. And what we're doing is sort of decoupling the two moving parts, the main moving parts that I talked about before. So we're decoupling the optimization of the user profile from the optimization of the personalization models, and each type of this sort of optimization has its own offline framework to do the optimizations. So for the optimizing the user profile, we have the user profile lab, and the staff will talk about it in depth in the next hour. And for optimizing the personalization models, we have the model learning framework, and I'll get into a bit of the details now. Okay, any questions? Okay, so let's talk about the model framework and what pains it tries to solve. So the goal of the offline modeling framework would be to simplify research and to automate our research. So to enable us sort of be agile in terms of introducing new models or testing existing models with other parameters and so forth. And we know that, everyone that does data science know that there are two aspects of modeling which are very crucial but are very time consuming. And the first aspect would be gathering the data. I'll give you an example in the next slide. And the second thing would be evaluating model performance. Okay, so, but the good thing, the advantage of those two is that they're sort of independent of the models. Okay, we can have some general frameworks or building blocks to solve this, to gather data and to evaluate our models. And then when we introduce a new model, we don't need to change anything in these sort of building blocks and can just reuse them. And that's what we're doing in the modeling framework. Okay, so let me give you an example of why gathering data is difficult. So in our use case in personalization models, what we essentially need to create is a label data set where we see the recommendations that are served to the user. We see all the information that the serving system sees. We need to see the user profile. We need to see the features of the content that we're recommending. And we want to see the response of the user. We want to see if the user engaged, if the user clicked or didn't click. Okay, so all this should be collected in a one unified label data set. And this is sort of the input to our personalization models. And to create this data set, what we need to do is to join 5 different Hive tables that contain the raw data. Okay. Now, as you know, we're serving tens of billions recommendations a day. Okay, so that means that the majority of these tables are huge. And for listings, it's basically all all the recommendations that we've served. The real listings are recommendations that we believe the user actually saw. So that's our way to sort of distinguish between recommendations that we served but no one saw and stuff that we served and actually the user saw. Clicks is obvious. User profile is basically we're storing for all users for each request the exact information that the serving layer had about the user at the time of the request. And add profile or document profile in case of Sphere and organic stack is the exact state of the recommendation in terms of its features that we had. Okay, so all these 5 types of informations are joined into a single data set. Now, when we did that before we had the modeling framework, creating this kind of data set could have taken us hours or even days. Okay, depends how long we need the data set to be. So we used Hive querying. It took us a lot of time. And it was also rather difficult to incorporate logic into this aggregation, into this creation of data sets. What kind of logic we want to apply, for example, we want to dedupe, we want to filter out some users that we suspect which are bots, and so forth. So we want to apply some logic that it wasn't really easily applied with our previous methods. And when each researcher creates its own data set, then it's being stored, sporadically. It can be reused. We wanted something that is available for everyone at each point of time, and something that is fresh and updates all the time. Okay, so I hope I convinced you that gathering data is pretty hard. Okay, and we want to automate that. The second thing I want to convince you is that evaluating model performance is also something that we want to sort of automate because we have a variety of evaluation metrics. We're actually adding metrics as we go. And for each evaluation metric, we want it to be available for everyone, regardless of which models we're using. And so if we have a new idea, we want to incorporate in sort of a joint system that can be then applied on all of our algorithms. And also, we want a mechanism that stores the metrics in a certain in a certain storage that we can have some future reference to these. Okay, so both of these are important. Now I will actually introduce the modeling framework that tries to solve these issues that I've described. Okay, so the modeling framework is basically a modular framework. It's based on Spark. It's in Scala Spark, and it has 5 major components. And these components are independent, and I will show you what we need to actually do when we're introducing a new model. What should be changed, what should not be changed. So what are the components of our modeling framework? The first one is a component that does the actual data collection. Okay, so what it does, it automates the process that I talked about before, which is very time consuming. Okay, so the output of this model would be a labeled data set, ready-to-use data set, which is fresh, and we can use it for our models. The second part is, the second and third part are actually related to the models that we're building. Okay, it's feature engineering and the model training. Okay, so these are the essence that we're changing when we try to test a new model. The fourth part would be the offline evaluation metrics. So it's sort of an independent model. The input to this module would be the predictions of our algorithms. And it doesn't really matter how the algorithm works. It just provides predictions, and we have the truth. We have the clicks or the non-clicks. And the evaluation metrics just takes these 2 types of data and sees how well the model did. Okay, but it's completely disjoint from the previous steps. And the final component is the model deployment. I will not get into it, but it helps us to automate bringing our models to production. But in this talk, we'll focus on the offline, so we'll not elaborate on that. Okay. So what happens when we want to introduce a new model or a new learning algorithm into this framework? The only thing that we actually need to change would be the feature engineering part and the model training. And very often, we don't even need to change the feature engineering. We're just changing the model itself. And essentially, the other building blocks, we're getting them for free in our process, okay? So not to get into details too much, but essentially, introducing a new model would just be implementing a new person model, implementing two methods. The one would be add columns that actually adds data. It's the feature engineering part. It adds an additional data that the model needs. And the second method would be the fit model. Fit model is train your model. Okay, so this applies the logic of how we're going to train our model, this new algorithm. Okay, so by just introducing a new implementation for that one, we're getting the full framework for free. And then to run our framework with the new model would just be to activate the Spark job that runs all these 4 or 5 components, depending if we're pushing it into production or not. So it does the data collection for us, it does the evaluation for us, and if needed, it also pushes to production. Okay, and this is configurable in terms of what data it gets, what model it uses. So if I just added a new model, I'm placing that model into this configuration, hyperparameters, and so forth. Yeah. Oh.
Hi. So you said the data collection is already included, and we don't need to touch it, but you said that you might want to add features, so the data collection might include new features, so you know what I mean? So you'll have to add them?
So that's a good question. So if I want to use new features, I have 2 ways of adding them. They can be added either in the data collection, and I will give you an example where usually they're added sort of implicitly. I will give an example in a second. But if they're very special features, then I need to do it in the feature engineering phase. So I'm taking the goal of the data collection is taking sort of the general data that everyone uses. And the feature engineering would be adding some data which is very specific to my algorithm. So for example, if I'm adding a new feature in the user profile, then it will be part of the data collection. But in fact, the way we're storing our user profiles for data collection, we're storing them in such a format that adding a new feature will not will not require any changes. We're storing sort of a blob of the user profile, and if a new feature is added, it's just added within this profile, and it's being written to the user profile table here. Okay, so it actually finds its way to our data set without actually changing anything. So this is a simple example. If we just add a feature to the user profile, it just propagates to our data set. But if we have new kind of features like embeddings and stuff like that, we'll need to incorporate them in the feature engineering phase. Okay. Yeah. So I will now explain about the data collection. It's sort of decoupled from the following stages. So it's a standalone process that generates on an hourly basis, generates data, writes them into a dedicated table, and then used by everyone. Exactly. Yeah. So I'll repeat the question. So the question was whether this process uses the data from production. Yeah. Mm-hmm. Right. So the question was, does it affect production? So it has 2 usages. The first usage is just research, which means that we're trying new algorithms, we're seeing what their evaluation offline metrics are, and this is like an iterative process. This is one usage. The second usage, which I it's not part of the talk. But the second usage of that is actually a production usage, where this framework is being run on a daily basis with the models that we already know that are improving our KPIs, which are not A/B tested. They're just like in production currently. And this framework is responsible for retraining our models on a daily basis and pushing them to production once they're trained. So in this sense, of course, it affects production. It actually updates the models in production on a daily basis. And for that, we need the last part, the model deployment. Okay. So model deployment says that it means that I've trained the model offline, and then I want the model to propagate to the serving layer. So it can be done in different ways, but the way we do it is propagating it through MySQL, and then from MySQL it's being read into the serving layer, and then the serving layer is aware of the newly updated models. Okay. So to Avi's question before, what are we actually doing with data collection? So I'll now dive into the data collection phase and the offline evaluation phase. But in any case, if you want more details, there is a very cool blog post by Shaked in Outbrain tech blog. It's called Taking the Pain Out of Data Science. So if you want more information, it's probably there. Okay, so a bit about the process of data collection. So as following the question I asked, as I said, what we're doing is have an hourly aggregation of the data that we need for our data sets, which are these 5 tables that I talked about before. We have the listings, real listings, clicks, user profile, and ad profile or document profile. And we're doing this aggregation on an hourly basis and placing this sort of already labeled, ready-to-use data set in a dedicated table, in a dedicated Hive table. Because this is implemented on top of Spark, and in Scala we can do whatever logic, we can introduce whatever logic we want, right? So we are supporting siloing, we're doing downsampling of our data, we're filtering out suspicious users, and other things as well. So we are running this hourly job and creating this dedicated table. And then the result would be that we have sort of labeled data sets available at each point of time. And now both the production flows that are actually deploying daily models to production can use this data, but also all our research iterations are able to use this data. Okay. Okay, and some details about our evaluation metrics, which as I mentioned before, we're introducing new metrics. We want them to be available for all the algorithms that are running in the system. So I'll tell you something about the specificity of our metrics. The goal of the offline metrics would be essentially to better predict what is going to happen in production, right? If I have an offline metric that is not aligned in what's happening in production, it's rather useless. So the challenge here was to find metrics that are aligned with our KPIs, with our sort of production KPIs. Now, the classical metrics, as you're probably aware of, are global. Okay, we have RMSE, which means square error. We have AUC metrics, and the question is, are they telling the full story, or we need to introduce other types of metrics? And I'll give you an example of why we need sort of other types of metrics as well. So just a quick overview of, for example, what AUC does. So the AUC metric, what it checks is whether my model was able to differentiate well between the clicks and the non-clicks. So what does it mean by differentiating well? It basically checks that my clicks got higher grades from the model, got higher scores from the model than my non-clicks, okay? So high AUC would be when a model is able to sort of separate the clicks from the non-clicks, and when it's not able to separate, it sort of gives kind of random scores, the AUC will be low, okay? But this is a very general, this takes into consideration the full data set, okay? And here, let me give you an example of what's happening. Let's say that we have a data set that comprises of only 2 users. Even before deep diving into it, what I'm going to show you is that this global metric of AUC is not aligned with, not necessarily aligned with what's going to happen in production, and then I'll show you a metric that would be aligned. Okay, so the use case showing here, we will see that introducing a new model improves AUC, but it doesn't really affect production. Okay, and then we'll see a metric where this new model doesn't affect this metric as well. So we won't be, so this new metric will be more aligned with what's going on in production. Hope it was clear. I'm not sure it was clear what I said. Okay, so asking questions is, yeah. Okay, so the example is as follows. We have 2 users, okay? User number 1, user number 2. Now we have our first model. We have our first algorithm. And what it did was to recommend 2 recommendations to user number 1, 2 recommendations to user number 2, and it assigns scores to each one of the recommendations, okay? So you have this, for user number 1, you have this music recommendation. The algorithm thought it is the score, the relevant score should be 0.4. And we have this technology something recommendation that the algorithm computed the relevant score to be 0.2. Okay, so these are the 2 recommendations for user number 1. Now for user number 2, the same algorithm recommends something else. Okay, and it recommends Star Wars, assigns a score of 0.2, and it recommends science fiction, assigning a score of 0.1. Now, as you can see, it doesn't really, the absolute scores here are not very important in this case. What's important is the order, right? So because the Star Wars got higher score than the science fiction, it will be presented first to the user. Okay? Now, we are now in an offline evaluation at a point where we're evaluating our models based on data that we already have, labeled data, right? So we know exactly what the user did. We know where the click was. And what happened with the click is that we're seeing that the click was on Star Wars by user number 2. And user number 1 didn't click on anything. Okay, now let's recall the metric that we talked about, the AUC metric. Whether will it give like a high value or it will give a low value? How is this model performing in terms of AUC? So what we're seeing is that, again, AUC tries to see if the clicks got higher scores than the non-clicks, right? And what we see that if we look at the full data set, right, so the good news is that this Star Wars recommendation got a higher score than the science fiction recommendation. Okay, these are the good news. But the bad news are that it got a lower score than this music recommendation that hasn't been clicked. Okay, so in this case, the AUC will not be that good. Okay, because sort of the model wasn't able to differentiate between the clicks and the non-clicks. Okay, but now I'm introducing a new model, a new algorithm. And this new algorithm does everything the way the old algorithm does, but the only change that happens here is that the new algorithm would assign a score of 0.6 to this click. Okay? But as you can see, nothing was changed in terms of recommendations, right? Like to the user, nothing changed. So in A/B testing or in live tests, we will not see any difference. But if we're looking at the AUC metric, suddenly it improved. Okay, why did it improve? Because suddenly this click got the highest scores among all the other recommendations in the system. Okay, and so the AUC is higher than before. Okay, so what the problem here is that when we compute this global AUC, we are looking at recommendations across users. We're looking at our full data set. While essentially what's important is what a single user is getting, and the order or the set of recommendation a single user is getting, right? So this motivated us to introduce or use new metrics, which are coming from actually widely used in information retrieval as well, in search, which are sort of request-based or user-based metrics, okay? And one such metric is it's called ordered pairs, but it's essentially computing AUC, the AUC metric that we just explained, but on a request level. So making sure that clicks are getting higher scores, but in the context of a single request or in the context of a single user, because what's happening between users is not very interesting to our system. Okay? And so in this metric, what we're going to see is that our two algorithms, remember we have like the previous algorithm, it got it gave a score of 0.2. The new algorithm gave a score of 0.6. But in terms of the request-based metrics, nothing changed. Okay? So the area under curve. But yeah, I can tell you in details offline what exactly it measures. I was explaining like on a very high level how it works. But okay, so essentially what we see is with the new matrix, with the new evaluation metric, which is based on request, we're seeing no change here. Where we wait, I think the slide is wrong. What I wanted to show here, no, it's good. Okay. But we are seeing a change when the algorithm actually changed the order of the recommendations. Okay. So in this case, where if our algorithm ranked first the science fiction and not the Star Wars, the AUC metric per request will say that it's worse than, the value is lower than if our algorithm ranked the Star Wars first. Okay, so it captures changes that will actually affect production, but it doesn't capture changes that will not affect production, which is what we want. We want the offline metric to be aligned with our online KPIs. Okay. So, and another small aspect is what I mentioned before, that we want our metrics to be stored for future reference. So this is also part of what this model of offline evaluation does. So it computes for every time it's being run, it computes the metrics, stores them in a dedicated table. We can then retrieve them and so forth.